Welcome to week 4.2. This video will reference the week 4.2.maxpat, which you can download and follow along with. And it covers two important objects in MaxMSP, the root object and the table object. And we'll start with the root object, which is in the bottom right corner of the patch. Now the root object is a router. It's a way of distributing your messages, lists in fact, to different places. So it's in that category of program control, the way a select or a split or some of those other objects we've come across are. The way root works is that you provide root with a number of arguments, usually integer arguments, but they don't have to be integer arguments. And root receives a list as input in its first inlet, and it compares the first element of that list to the arguments. And if there's a match between the first element in the list and one of the arguments, it will send the remainder of the list out the outlet that is basically that represents that argument. In other words, if I've got a root here with arguments 1, 2, 3, 4. If my list comes in and the first element is 1, then it sends the remainder of the list out the first outlet. If the first element is 2, it goes out the second outlet, and so on. So it's doing a comparison, looking at the first element and sending the remainder out. If there's no match at all, then it sends the entire list out the final outlet. Okay? And the inlets in root can be used to alter the arguments. So that's what they're for. But normally your messages will go into the first inlet. So in this little example, I have the outputs for these matches of 1, 2, 3, 4 going out. Well, 1, 2, and 3 certainly are going out to different make notes on different channels. So if we click on this message 1, 60, 100, it will match with the 1. The root will strip off the 1 and send the remaining 60, 100 out to make a note. If we send this one out to 165, it will match with 2, and it will send it out to the second make note, going out to channel 2. You notice it's a different timbre, it's also a much higher pitch. Maybe we should make it something a little more reasonable. Okay, that's on channel 2. And this one, channel 5, goes nowhere except to a print which says no out, and you can see that the entire message is there printed. Okay, so that's the way root works. It's fairly simple, but it only works with lists, because if you send it just an integer in, it will make the match, but there's nothing left for it to send out. There is an object called root pass that you can look at if you want, and root pass will make a match and then send the entire message out, not just the remainder of the message out. So this particular object is very useful for distributing your messages if you want them to go multiple places. Okay, now tables. Tables are a very important data structure in MaxMSP. Up until this point, we really haven't had any data structures other than individual places to store data, like an int object or a float object. And all programming languages need to support the storage of data. And so one of the ways you can store data is with a table. And I'm just going to click on this table, double click on the table icon, table object, and you'll see that it provides me with a little graphical display. And I'm actually going to drag my mouse in the table. And what you see here is a whole bunch of values that have been stored in this table. And if I click on them, I can see at the top, it actually shows me where my mouse is, so I get an idea. that in the X position I'm at 36, and in the Y position I'm at 80. This is actually by default a 127 by 127 table. In other words, you can think of it as a list of 127 values which can store numbers in them between 0 and 127. So the x-axis we think about as being the index of the table. Where in the table is this number stored? And the y-axis is the value that's being stored there. In essence, a table is really just an array for those of you who have done other programming languages. And we access the elements of a table by using the index. In other words, if we want the first element of the table, we understand that it is in position 0. If we want the second element, we understand it's in position 1 in the table. Because it's computers, we always start counting with 0. If we want the very last item in this table, it is in the 127th position. It's the 127th element in this table. Okay? So tables can be of any size, and they can hold values of any amount. Right? So it doesn't have to be limited to 127 by 127. You could have a table with a size of 10. In other words, it's only holding 10 numbers, but it could hold values between negative 32,000 and positive 32,000. You can put floats in tables, but integers are almost exclusively you use integers in tables. Okay, so that's how a table works. I'm just going to move this over a little bit. When we click on a table in edit mode, and we bring up the inspector, Command I, among all the things we find out about the table, I'm going to move this over just a little bit more so you can see. One of the most important things we need to know about a table is what is the table range and what is the table size. You can see here we can have signed values, so we can have positive and negative as well. But essentially we're going to use, tables are going to be used with integers. Right? So we could make the table range 24. That simply means that we can store values in this table between 0 and maybe take a 25. And the table size can be any size. It can be small, it can be large, it can be 100,000, it can be 10. Right? So I've made this table much, much smaller. I've made it because I don't really need 127 values in my table. I only need 10 values in my table, and I know that the numbers I'm going to store in my table are between 0 and 24. So that range is fine. If I want to, I can make it larger, but there's a reason for making it small, and that is that when I double click on this table now and it comes up, it's actually quite easy to edit this. I can see these values, and I can see at the top. I can see what values I'm generating in my table. So I'm just sort of creating some sort of strange scale here in my table. So again, when we're looking at this, if I want to either store or retrieve this value, this is the 0th value in the table, this is the first value in the table, this is the second value, third value, all the way up to the 9th value in the table, because there's a size of 10. Okay? Now I'm going to pull this table out, pull it down here, and I'm going to put an integer into it, an int box, into this table, and see what I get out. Another integer box. And I will make it visible just so you can see as I'm doing this. If I type 0, I get out 0. If I type 1, I get out 4. Why is that? Well, incoming value to a table is asking for the value that's in that particular index. So 2, I'm going to expect to get a value of 8. 2 is 8, 3 is 10, 4 is 12, 5 is 13. These are the values that I put into the table. Okay? So a single integer going into a table is basically a way of retrieving values from the table. And it retrieves value by looking at the index and pulling and retrieving the value, outputting the value that is at that index. Now, what happens if I want to set values into a table? Well, rather than using a single integer, which will pull values out, I put a list in. And so if I put a message in that says, for a 5, 8, what happens? Well, the 5th element in my table now has a value of 8. How about 6, 1? The 6th value in my table now has a value of 1. So I use lists of 2, a list of 2 integers, to indicate what element in the table, what index in the table, and what new value it should have. So I can both create tables by putting lists in them, and I can retrieve values from tables. So, you know, this is extremely useful if you want to be able to store data somewhere, and not just a single integer, but a whole series of integers. And then you want to be able to retrieve those values at a later time. So this is really a storage object. Okay, just a couple things with tables. There is a warning here. Well, it's not really a warning, it's an important. And that is that tables are not persistent unless you make them persistent. In other words, when you close this week 4.2 file and open it again, your table will be empty. Unless you go into your inspector, I'm going to click on this table, go into the inspector, and scroll down to where it says Save Data with Patcher. This is a very important thing if you spent a long time building tables and you don't click this. So now, because I've clicked that, when I save this file and close it and open it again, the table will remember its last state. Whatever data was in the table when I last saved it will be retained and come back in. For the next assignment, one of the things that students sometimes do is they make tables which store scales in them, and then access those scales. If they don't want music to be random and they want music to be generated within scale, then you can use tables, but you must remember to save your table once you've created it, so that when I open the patch to mark it, I just don't have blank tables. Okay? You can also give names to tables as an argument. This is a table with a name, and it's with a name is its first argument. And when you have a table with a name, you can create another table with a name, the same name, and they will both reference the same data. So for example, this table I think is saved, and it's got this nice curve. It's got a lot of data in here. If somewhere in my patch I type table and give it an argument that is exactly the same as that, and I double click on it, it has the same data as the other one has. That's this one, and that's this one. If I change one, I'll be changing the other. So they refer to the same data in memory. Now, there's lots of times where this is really useful. Let's say you have a part of a patch which is setting values into a table or storing values in a table, and in a different part of the patch you want to pull data out of that table. You can simply reference the same table by giving it the argument of a name. Okay? And lastly, with tables, there is something called an I table, which is a table that actually just is graphically sitting on your screen. And I made a graphical I table in here. I can make it a little bit smaller. Oops, I didn't mean to edit it, but I did. You can make it nice and small. See if I can recreate what I had in here. Okay. Tables. So this is just a little short example of a table and showing you how you can programmatically put values into a table. So let's first of all check that this table is empty. And I could check to see what kind of dimensions this particular table has by clicking on the table, going Command I, looking down at the bottom, and seeing that it is a table range of 128 and a table size of 20. Okay. So just to reiterate, a table size of 20 means that there are 20 elements in the table, indexed 0 through 19, and the range of values is 0 through 127, a range of 128. Okay, so in this little patch, you can see that, I'm just going to get rid of that, not sure why it's there. Right, you can see that I send a number in, and then I have a trigger, and the trigger does two things. First of all, it stores the integer, the value that I put into the table, puts it into an int box, which we know can store numbers, and then it bangs the counter, and the counter also has a trigger, and that trigger does two things. It first of all bangs out the integer I just stored and puts it into a pack object, and then it sends the counter number into the pack object. This pack object then has a counter number, a number from the counter, and the value that I put in. So if I were to do something like this, say 60, 62, 63, 65, 66, 68, 70, 72, 73, 75, let's just go crazy now, 80, 100, 99. Okay, and I'm just entering these values, and I'm going to open up my table now. And what you can see is the data that I put in this table, right, with the indexes that the counter supplied. Okay? Now, if I wanted to, let's do something really quickly. Let's then put it an I box here, put it into the table. These I was intending to be pitches, so why don't we just send them out over here, up here, into this make note, and see what happens. There's 0, 1, this is where I went a bit crazy. Right? So you can see that I can store values in a table using something like this, and then I can retrieve those values out of the table. And it should be clear that all that's happening is these values. When I say 0, it brings out the first one. When I send in 1, it brings out the second one, and so on. So I can, temporarily, I could sort of create my own little sequencer where I play notes, and as I'm playing notes on a keyboard, I'm recording them into a table so that later on I can play them back. Okay, so that's table. It's a powerful object. As I say, it's very useful for doing things like setting up scales, where you could, for example, just set up 1 octave of a scale and then take those pitches out of that table and then add some other value to them, like add 60 to them. So if you had a table that had 0, 2, 4, 5, 7, 9, 11, and you took values out of the table randomly and added 60 to them, you would be limiting yourself to the notes of a major scale, a C major scale, because you would only get 60, 62, 64, 65, 67, 69, 71 out of that. So you get C, D, E, F, G, A, B. Okay? So, and then if you wanted a minor scale, you could, use 0, 2, 3, 5, 7, 8, and so on. So and you can figure those things out yourself. So that's table and route or root. Useful object. Table, probably an essential component for your next assignment. If you want to do anything that deals with scales or modes or things of that sort. And that's it for this tutorial.